Hi, Professor.
Hey guys,
How are you today?
your name is different.
Oh, it is.
You're
That's
not Classy Kane, are you?
no, that's what I have on all of my social media.
Oh, is that right?
Yeah, and my
You're
sister, my
you're
sister.
Robert, right?
Robert,
Yeah,
yes.
okay, that's what I thought. All right, all right. I gotta remember Classy Kane is Robert. All right, that's fine. Let's see. Hey, Evie.
Oh, hello.
We're just waiting for more people to show up. It's exactly 11 right now. We're all starting to show up. Suresh. All right. Awesome. Everybody's showing up right on time. What do we got? One,
Go,
two,
Professor.
three. We got 9. Pretty good. Let's give it one more minute and we'll get started.
Oof.
There's one more. All right. I think we're pretty much all here. Let's get started. Okay, a couple things from last time. I wanted to talk just a little more about the repeated eigenvalue case. I tried to type stuff out on Sakai just in like a text email, and it's really painful to type matrices and things in a text email. And I didn't want to take the time to write a LaTeX document with homework help, so I figured I'd just go over it now. So let's talk a little bit more about that repeated eigenvalue case. It's really not that important, and the trace determinant plane, I think, shows us why it's not that important. It only happens for very, very specific values, and just on that parabola in the trace determinant plane. And if you tweak your system at all, any amount, you end up leaving the parabola and going into one of the other regions. So what you in nature, you never really see it. Um, so in some sense, it's not that all important. Same with the zero eigenvalue case. In nature, you never see zero eigenvalues because that's such a specific situation. If your system is tweaked even the tiniest bit, then you go off that line. So now with that said, as a teacher, I'm compelled to correct errors that I've made in class. And I know that was extremely confusing last time. And so I'm going to just go over it again one more time real quick. Let me just pull up, share my screen. And let's see. Just give me a minute to share my screen. Share. Hey, that just worked. Okay, this is where we were at last time. Does everybody see that? Let me rearrange my screens here. Hold on one second. Okay. Can you all see the iPad screen? Just nod. Yeah, good, okay. All right, and I gotta arrange all my monitors in the right way. I'm gonna pull up the chat window. If anybody has questions, either if you have questions, either turn your mic on or just do it right into the group chat. It's probably actually better if you just turn your mic on and just yell out your questions. Because if you type your questions into the chat, I may not see it right away if I'm just talking and babbling and staring at my iPad screen. So I will try to glance up occasionally and look at the chat window. All right, looking at the iPad screen now. So I mistakenly said something. In fact, I wrote the right thing in class, and then I went back and corrected what I thought must have been true. So this is what I had said in class. I just was reminding you of the theorem was right here from the book, but in the book, they don't have C1 and C2. That's not actually there. In the book, it's just e to the lambda t v0 plus t e to the lambda t v1, okay? And it's this thing here, the initial condition, which is where your arbitrary constants here, your initial condition, you just write that as x0, y0. And if you keep it arbitrary, just x0 and y0, you end up with your general solution. And then you can solve for x0 and y0 if you have a specific initial condition. And I think this is where some of the confusion came in that I really want to go over from last time. So I'm going to redo this problem, the one we tried to do last time, the one I completely got wrong because I wasn't doing it right. What we did last time was mostly correct. It was just the very, very last step that that was off. And so when I entered into WebWork, I got the wrong answer because I was doing it wrong. So here was the problem. It was -3, 1, 0, -3, and -2, -1 were the initial conditions. So let's see, I'm going to start a new document here. So we got -3, right in black, -3, sorry, I'm still working out my technology. -3, 1, 0, -3. That's my matrix. And my initial condition is -2, -1. Right? So if they tell you to do, they say that that the solution, well, first let's get the eigenvalue. It's the same calculation we did last time. So we just subtract lambda from the thing on the diagonal. We take the determinant, and that gives us -3 minus lambda squared equals 0, which tells us lambda equals -3. Okay, it's just the stuff on the diagonal, which we already knew. All right. Now what they say is the solution looks like e to the lambda t, so that's e to the -3t times v0 plus t e to the lambda t, that's -3t times v1. So there's the general solution. Okay. Now v0, if we keep things arbitrary, that's just x0, y0. And v1, you get that by doing a minus lambda I times v0. Okay, so let's compute that. A minus lambda I. So again, A is this matrix. So if I just subtract -3 from the stuff on the diagonal here and here, well, -3 minus -3 is just going to give us zeros on the diagonal. So again, we did this in class last time, but we ended up with 0, 1, 0, 0 for a minus lambda I, and v0 is x0, y0. So now that just gives us the vector y0, 0. Okay, again, we did all this last time. Just yell if there's any questions about this, but this is as far as we got last time. Okay, now let's write down what that means. The general solution is now e to the -3t times x0, y0 plus t e to the -3t times y0, 0. Okay, got that? And I did not write that last time. I put that in the email. But going further, actually, there's stuff I didn't email you about, which are how you figure out x0, y0. Obviously, you need an initial condition for that. So let's go through that calculation. Initial condition happens when t equals 0. Then we should be getting the vector -2, -1. That's the one they give us. So we have -2, -1 equals e to the 0 times x0, y0 plus 0 e to the 0 times y0, y0, 0. Okay? And that tells us, not surprisingly, that x0, y0 is minus 2, minus 1. Okay, we also did that last time. We said, hey, the initial condition they gave us should just be, should just go right here, right? There's our initial condition. That's what the book says. It's V0 is our initial condition, okay? All right, now here was the missing step. There's one little missing step. Is now we know what x0, y0 is. We got to go all the way back to here and plug everything in. So not only do we plug x0, y0 in here, but we also have to plug x0, y0 in here. That's what we were missing last time. So the final answer is e to the minus 3t times x0, y0, that's minus 2, minus 1, plus t e to the minus 3t times, looking back up here, we have y0, 0 up there, okay? So we got to put y0, 0 down in this blank vector. Y0 is minus 1, and we have a 0 down there. So this is what I was missing last time. When I entered it into WebWork, I only entered this first term, and it told me I was wrong because I was forgetting about the second term, which is also necessary. So the book's correct. WebWork is actually correct. It was me that was wrong because I was forgetting about the necessity of that second term. That second term is necessary even though the initial condition happens when t equals 0. This is still the correct answer for the general solution for that initial condition. You need everything there. Yeah, Sarish, I see you've raised your hand.
What about the scalars C1 and C2? Do those also just get like tossed in here?
Oh, the scalars aren't there. If you look at the original formula and the original, going back to the book, let's see if I can go back there. So when I wrote this yesterday, that C1 and C2, I wrote that C1 and that C2 there. They weren't there. I shouldn't have put it. I should never have put them in there. Those two arbitrary constants are just here. They're really the two arbitrary. Every solution to initial condition for a 2x2 matrix depends on two arbitrary constants. And in every other case, we use C1, C0 and C1 or C1 and C2, and they were coefficients of two terms that came up. In this particular case, when you have repeated eigenvalues, your two arbitrary constants are just the x and y coordinate of the initial condition. Those are where your arbitrary constants are. Okay, so this repeated eigenvalue case is really different than all the other cases, and that's one way it's different is that those arbitrary constants are in different places.
I see.
All right, so hopefully, I hope that clears up some confusion. So let's see, going back to here. So this was the complete solution. If you have minus 3, 1, 0, minus 3 with an initial condition of minus 2, 1, so it's at the top of the page, then the answer is way down here at the bottom. We've got e to the minus 3t, because minus 3 is the eigenvalue. We've got minus 2, 1, right where we thought it should be last time, where v0 was. And what we didn't do last time was include the second term there, where you have t e to the minus 3t and y0, 0 as v1. Okay? And one other nice thing is that that vector is always an eigenvector of the system, which means this actually can help us plot things too. So since we know minus 1, 0 is an eigenvector, if I plot minus 1, 0, minus 1, comma 0 is just on the horizontal axis there, right? That's minus 1, 0 is right over here. Minus 1, 0 is that point, right? So that horizontal axis is the eigenspace corresponding to the eigenvector of -3. Right now, since that eigenvalue of -3, since the eigenvalue is negative, that means on that horizontal axis, things are going toward the origin, because this corresponds to lambda equals -3. Because it's negative, it goes toward the origin. And then it's not clear what things look like off of this, but they're going to go in some sort of S curve, either like that, or the S will be oriented the opposite way. How can we tell if the S looks like that, or if it looks like this one? Anybody have any ideas how we might tell?
Is it based on the sign of the eigenvalue? Or no?
I don't think you can look at it by looking at the eigenvalues or the eigenvectors, actually. You got to just look back at the original matrix. Does anybody remember when we did complex eigenvalues? Things were either spiraling clockwise or counterclockwise. Do we remember how it was a quick check to determine if things were clockwise or counterclockwise?
Was that the real component?
No, it wasn't the real component. No, in fact, you can't tell just by looking at the eigenvalues and eigenvectors. You have to use the original matrix. How did we use the original matrix to check if things were clockwise or counterclockwise?
Did you just like plug in values?
Yeah, just plug in a point. Let's just plug in a point like right up here on the y-axis to the original matrix and see, do we get a vector that points to the left or the right? If it points to the left, then it's exactly this picture I've drawn. If it points to the right, the S's go the other way. Okay, so let's just go back. Let's just finish this problem, even though they didn't ask for it. Let's really kill this problem. So let's plug in a vector all the way back at the very beginning. We've got -3, 1, 0, -3 as our matrix. So let's go back to the bottom. -3, 1, 0, -3. That's our original matrix. Give me a point on the y-axis up there, an easy one.
0, 1.
0, 1. There's an easy one. Good. If we multiply those, what do we get?
1, -3.
1, -3. Good. All right. So let me see if I can erase some stuff we did. So 1, -3. Up here at the point 0, 1, we've got 1 over in the positive x direction and, oops, -1 in the -3 in the y direction. So that points down to the right. Okay, positive x, negative y. So that's telling me these s's have to do that. And then it's got to be opposite in the other half. So this would be the phase portrait of this kind of system. Good? We okay? On an exam, I might ask you to go even further. I might ask you to say, for the initial conditions 0, 1, plot, give me a rough sketch of x versus time and y versus time. Let's go, we might as well just really kill this problem. If 0, 1 is my initial condition, that means x starts out being 0. So x starts out here. And then what happens, let's look at this point right here. What happens to x as time increases? So I start up here at this point. Just think about what happens to x as time increases. I'm going to go toward the origin along a curve like this. So what's happening to x?
X briefly increases, then decreases.
And decreases, and it gets closer and closer and closer to 0, right? And the size of those tangent vectors gets smaller and smaller and smaller. Okay, so x briefly increases, and then it decreases. It never touches 0. It's just asymptotic to 0, right? It levels off. What about y? What does y do? What does y start at? And then what happens to y?
It just goes straight down.
Yeah, it's just y just gets smaller and smaller and smaller. So it starts up here at 1. At 1, and it just decreases, getting smaller and smaller and smaller. Good. That's about everything I could possibly ask you with a question with repeated eigenvalues. All right. Hopefully I've cleared up some confusion. Well, let's move on. Are there any questions about the web work problems you do today? Again, they were Weber problems I assigned before. I just reassigned them to you, hoping you would use the trace determinant plane that we talked about last time to redo those problems and see if you could figure out which phase portrait corresponded to which system using the trace determinant plane.
Yeah, do you mind going through like number 3? Like
Number 3?
yeah, I think the first 2 are okay, but like the third one really stuck me for a while.
Number 3. So I have it up here. This is homework 11. Oop, I'm timed out. Give me a sec here. Homework 11, problem 3. And you want to go over like how to distinguish between these? Sure. All right, let me just remind you real quick. The trace determinant plane. Whoa, whoa, whoa. We have, sorry, it's not as easy to draw on an iPad as you would think. We have the trace determinant, okay. And then we have the equation t squared equals 4, t squared minus 4d is the discriminant. So the parabola that you're plotting up here is d equals t squared over 4. That's this parabola. And it's key that you really understand that what that means. And then we talked last time fairly extensively about how the horizontal axis, the t-axis, the positive d-axis, and each side of the parabola, they really divide the plane into these 1, 2, 3, 4, 5 different regions where you have different behavior, okay? So with each of these problems on the homework, you just have to compute T and D and figure out which region of the plane you're in. And then that should...
Just my view, but your screen's frozen on the iPad. Oh, there we go. Now it just went. Okay. Sorry.
There might be a lag. Probably not your screen. Probably my internet connection. My internet connection isn't great. Did it catch up? We're good? Okay, cool.
Yeah, it just caught up.
All right. First one on the problem 3 on homework 11 was 2002. So what's the trace for that?
4.
4, right? Just the sum of those things on the diagonal, which is 4. And what's the determinant?
Also 4.
Also 4. Okay. So since the determinant is positive, since they're both positive, we're in somewhere in the first quadrant up there, the positive quadrant. So it's just a question of whether or not we're above that parabola, below that parabola, or on that parabola. So we've got to compute d and t squared over 4 and just decide which one of those is greater. So d is 4. T squared over 4 is 4 times 4 over 4 is just 4. So it turns out they're equal. Since they're equal, where are we?
We're on the parabola.
We're on the parabola. Yeah, we're over here somewhere up there on the parabola at 4, 4 in the trace determinant plane. And now looking at the pictures that they've given us, it looks to me like, so on the parabola, that's the repeated eigenvalue case. And it looks to me like that is Probably A. I would guess that's A.
Yeah, but the answer is D.
Oh, you know what? Yeah, both A and D could be repeated eigenvalue cases. So now I'm looking at the pictures on the web work. I don't know if you all want to pull that up separately. Um, I guess I could share that screen. Let's see. There we go. All right, you should all see my WebWork screen now. Do you see my WebWork screen?
Yeah.
Okay. And let's see if I zoom in on that. Did you see those get bigger? I want to make sure my technology is working here.
Yeah, I think the answer I got, like the order is different. So what I got was your C.
Yeah. Oh, your order is different. Oh, yeah.
Yeah, yeah.
It looks to me like both A and D there are both repeated eigenvalue cases, but there's a really important difference. On A, the arrows are pointing away from the origin, and on D, the arrows point toward the origin. So if we look at 2002, the eigenvalues are just two repeated eigenvalues, both 2. Since they're both positive, things go away from the origin. So the answer for me will be A. But yeah, they may have shown you these pictures in a different order on yours.
Yeah, like I tried out different combinations because I couldn't
Yeah.
figure out why it's not right.
Yeah.
And the correct answer it gave me is for the first one, the answer is C, like your C.
Oh, my C.
Yeah.
Oh, but are your equations in a different order?
No, it's the same one.
Huh.
So I got really confused on that one.
Doesn't look like it should be C. Looks to me like let me check what I get. Let's see if I'm thinking that one should be A. Number 2 is also a repeated eigenvalue case, but the eigenvalues are negative, so things point toward the origin. So things there are, I would say D. Let's look at 3 and 4. On 3, we have the matrix 1, 1, 1, 0. Looks to me. So let's see.
I think it should be 1101 because the
1,
second one
1,
is
0, 1. Yes, yes, yes. Thank you. So back to my iPad screen, we've got 1, 1, 0, 1. So the trace is 2. The determinant is 1. So D is 1. And T squared over 4 is 2 squared over 4 is also 1. So they're equal. Are all these repeated eigenvalues? Damn it. I think I asked you 4 questions with repeated eigenvalues. So the trace determinant plane doesn't really help you a whole lot with this problem.
yeah.
Which was the whole point of asking you this problem. So I apologize. This was a terrible question to ask you as an exercise in using the trace determinant plane.
Okay, so we don't really need to use the trace determinant plane to decide?
Well, yeah, that's what I was intending, but obviously this was a terrible question. Let's look at this one though, 1101. So we know the eigenvalue is, is 1. So lambda is 1. So let's get the eigenvector real quick, and I think you'll see what happens here. If I have a guess what's going to happen if we look at the eigenvector. So the eigenvector, we're going to get 1101 times xy equals 1 times xy. So that gives us x plus y equals x and y equals y. Y equals y tells us nothing, right? And this tells us that y has to equal 0. So the x-axis is, if y equals 0, the x-axis is our eigenspace. And that's true for all these. Crap. What's going on? Oh, I see what's going on. Okay. All right, so for this problem, we've got a single eigenvector, which is of the x-axis. Let's go back and do the first problem, this one here. Let's keep going with this. We've got 2, 0, 0, 2. If we compute the eigenspace there, we do this calculation. So we get 2x equals 2x and 2y equals 2y. All right, describe for me all the points in the plane where 2x equals 2x and 2y equals 2y.
The XY line, or the line X equals Y, sorry.
I think it's more than that.
It's just everything, right?
Everything.
Yeah, for every value of x, 2x equals 2x, and for every value of y, 2y equals 2y. That tells you every vector is an eigenvector. Remember, when you have repeated eigenvalues, you have two possible cases. Either you have just a line of eigenvalues, and the other things move along these S-curves, or every vector is an eigenvector, and in which case things just move toward the origin or away from the origin, okay? So in this, what we found and just found out in this case right here, every vector is an eigenvector, and you have a positive eigenvalue. So everything just moves away from the origin. And so that is answer C. I'm going to revise my answer. That's C. C is the only picture where every vector is an eigenvector and things are moving directly away from the origin. And that same thing is going to happen in 2. In 2, every vector is an eigenvector, but everything's moving toward the origin. That's looking like B is my answer. So let me share that screen again. All right, so I switched my answers to 1 and 2 to C and B. On number 3, it's the one I did a minute ago. We found there was only a line of eigenvalues on the x-axis, and the only a line of eigenvectors on the x-axis, and the corresponding eigenvalue is 1, which is positive. So that tells me things move away from the origin on the x-axis. So that's C. Sorry, that's A. And by process of elimination, I'm going to guess this one's D. And so we can check that, and hooray! All right. So this was sorry, I apologize, because this was a terrible question to ask you. The whole point of this, asking you these questions again, was for you to understand the trace determinant plane. Timing-wise, it's not so bad, because the last thing we did before that was the repeated eigenvalue case. So it turns out this problem is more about understanding repeated eigenvalues than the trace determinant plane, which is fine since we've been talking about the repeated eigenvalues situation as well.
Okay.
Everybody understand what's going on here? So 2 of the 4 problems you're given here have repeated eigenvalues where every vector is an eigenvector, which means everything points toward the origin or away from the origin. The other 2 systems just have a single line of eigenvectors, and on one of those, things move toward the origin, and the other things move away from the origin, and that's enough information to narrow down which picture is correct. Any other questions about this one? Good? Can we move on? Thumbs up, thumbs down, thumbs up. Thank you, Robert. Robert, your name changed back.
I know, I changed it.
All right, good. Let's move on. I've got to share my screen again. Hold on a minute. New via cable. Good. Perfect. Great. Okay. Again, we've got this trace determinant plane. We've got this parabola. Parabola is the parabola d equals t squared over 4. And you should know what the picture looks like in the different portions of this plane. Down at the bottom, these are the saddles. The sources are in the positive quadrant and the sinks are in the negative quadrant. So this is a source and this is a spiral source. And then sink, spiral sink. And on that positive D axis, those are the centers. Okay. And then we have repeated eigenvalues on the parabola and 0 eigenvalues on the T axis. This is T and D. All right. The remainder of this chapter, we're still in the same section, which is section 3.7 of the book. And the remainder of this section, we're looking at specific systems and using the trace determinant plane to talk about specific kinds of systems. So we skipped section 3.6, but now actually I want to do it retroactively and use the trace determinant plane to talk about the material that's in 3.6. So 3.6 is all about going back to the harmonic oscillator, which is a typical second order differential equation that we're going to convert to a first order system. So just to remind you, we did some Newton's laws in class, and we came up with this equation for a spring. So the picture is you've got a wall, you've got your floor, you've got a box here of a certain mass. It's attached to a spring. Okay, that spring has some spring constant K, and that gave us the equation 0 equals. Sorry, one sec. Sorry, my technology's being funny again. 0 equals m, the mass, times the second derivative, okay, plus the constant times y. Okay, that was the situation we first did where we used Newton's laws. That mass times d squared y dt squared, that should look really familiar if you've had a high school physics class. That's just Newton's laws that say F equals ma, right? M, a is the acceleration. Acceleration is second derivative with respect to position. This is our y-axis here. So y is position. D squared y dt squared is acceleration. This was the situation where we had a frictionless mass in a spring. If you have friction, then the friction acts in direct proportionality to the velocity. So you end up with this other term, b dy dt, where b is your friction. Friction acts to retard the oscillation, the motion of the mass there that's on the spring. So sometimes it's called the damping coefficient. Okay, and the one, so just to make this physically realistic, so they're not just abstract variables and numbers, you should know that we're dealing with a mass, and since it's a physical object, mass is greater than 0. Since it's a physical spring, every spring has a spring constant, a positive spring constant, and friction is always greater than or equal to 0. We can think about the case where there's no friction by setting b equal to 0. Okay, so we have these 3 assumptions here that are going to be really key for understanding where in the trace determinant plane we are. All right, now here's our system. That's a typical second order system. We've looked at this system before. How do we convert this to it's a second order equation. How do we convert the second order equation to a first order system? What do we have to do?
Add a velocity term.
Yeah, we need a velocity term. So we say dy dt is our velocity. And then dv dt is, well, let's see, we'd have to solve for dy. So up here, we'd have to solve for dy dt. It's a little hard to write in here. So dy dt is minus m over b d squared y dt squared Sorry, I'm really squeezing it in there. Minus k over b y. So going back down here, d squared y dt squared, that's just the derivative of the velocity. So we get minus m over b times, sorry, what did I do? Shoot, I solved for the wrong thing. I wanted to solve for dy dt. Sorry about that. Let's see. Give me a sec here. Okay, let's solve here. So d squared y dt squared is going to be equal to minus b over m dy dt minus k over m. So,
Now I have the full Rhino object, which includes all of its attributes and stuff. So attributes are what, like,
what
the
the heck
human
just
bucket
happened?
is interested in, like, extracting the attributes.
Sorry, I'm having technological issues again. I hope you're all seeing this. You all see my iPad screen? Because it disappeared on my screen for a little bit. Okay. All right. So this is what we get here. So d squared y dt squared, that's just, that's dv dt. So I'm just going to rewrite exactly what I have over there. We've got minus b over m. Dy dt is just v minus k over m y. Good. We've done this before like 50,000 times, so hopefully you're all bored. All right, so that's my system right there. And now we can rewrite this as a matrix. So we have dy dt. So my handwriting's deteriorating now. Not only am I having technical difficulties, but I'm having difficulties with my handwriting. Okay, dy dt dv dt equals, we have this matrix, which is times y b. And what matrix do we get? We get 0, 1, and minus k over m minus b over m. Does that look okay? All right. My apologies that took so long. All right, now you guys are up. What's the trace?
Negative b over m.
Yeah, it's the sum of the values in the diagonal. So it's 0 plus negative b over m, which is just negative b over m. Good. What's the determinant?
K over m.
Yeah, positive k over m. K over m. Okay, then over here. Trace determinant, okay? So you have to do 0 times minus b over m minus negative k over m times b, and that gives you positive k over m. Good. So here's the trace, here's the determinant. Now, minus b over m, let's go back to our basic assumptions. B is greater than or equal to 0. M is greater than 0, which means t is greater than or equal to 0, right? If b is 0, we just get 0. If b, sorry, and then we have a negative sign. So we get b is less than or equal. We get minus b over m is less than or equal to 0. Okay, but d is the ratio of two things that are strictly positive. Neither of those can be 0, so d is strictly greater than 0. Right. So if t is greater than or equal, is less than or equal to 0. Here's t. Here's d. So where are we in this picture?
We're in the fourth quadrant, right?
think you did
I
this
know.
last time, Suresh.
No,
I think
no,
you know
no.
the
It's
answer,
like
but you get the quadrants wrong.
Nothing.
Which quadrant?
Quadrant one.
We're in the second quadrant. Right?
Second quadrant. Good. All right.
Okay,
So we're
yeah.
somewhere in the second quadrant. Okay. And we might be on the d-axis, right? Because t is less than or equal to 0. When t equals 0, we're on the d-axis. But we can't be on the t-axis because d is strictly greater than 0. Okay. So we have 3 possibilities. So let's just look at the possibilities here. Either, let me do kind of a blow up of that second quadrant. So we've got so either we have a sink, so things are moving toward the origin, or we have a spiral sink, or if we're on this d-axis, we might have a center tangency. Okay. And one more possibility is that we might have a line of eigenvalues like that, okay? All of these have names, and all of these correspond to physical interpretations of a mass on a spring. And the physical interpretations and the names should reflect each other. So if we're on this axis, here, that's called undamped. Okay, and what's happening there? This phase plane is the y-axis, the horizontal. On each of these little phase planes, let's just look at this case in particular. What we're plotting here is y versus v. And we're saying things move around the origin constantly. So if you just think about the y coordinate there, that horizontal coordinate, if you're going around the origin, around and around the origin, then the y coordinate is just going smaller, bigger, smaller, bigger, smaller, bigger. And that should remind you of what happens if you have a mass on a spring and it's oscillating and there's no friction. It's just going to go left, right, forever, right? Okay. So that's the undamped. Undamped means frictionless. This situation over here where things spiral toward the origin, that's called underdamped. And the opposite is this situation here, which is called overdamped. So underdamped and overdamped, if there's not enough friction to prevent, so first of all, if there is some friction, any friction at all, you know this spring is going to stop oscillating eventually, right? The oscillations will get smaller and smaller and smaller. Okay, so in all these other cases, you know you have a sink, right? But if it's underdamped, it means there's not enough friction to prevent some oscillations. So it's mass on the spring goes left, right, but those oscillations get smaller and smaller and smaller. So the term underdamped means there's not enough friction to prevent oscillations. Okay? Overdamped means there's more than enough friction to prevent oscillations. So if you think of a mass on a spring and there's a lot of friction, right? So maybe this mass is moving through a really, really viscous liquid or something, a really thick liquid. Then what's going to happen? You've got your wall here and your mass here. Does everybody see my picture in the corner or something? Can you see me? Yeah. So you've got a wall here and a mass here, and there's so much friction. Even if I pull this mass away from the wall, then there's so much friction, it's just going to slowly move to the rest position and stop at rest. Okay, the spring pulls it back to the rest position, but the friction prevents it from going past the rest position and then oscillating. Right? That's what's happening in that overdamped situation. And then the intermediate situation, that's called critically damped. Critically damped means there's just enough friction so that I pull this mass away from the wall, okay? There's just enough friction so that I prevent oscillations, but not enough friction for it to not move past the rest position. So again, I have this mass, I pull it away from the wall, I let it go, and it starts moving back toward rest, back toward rest, back toward rest. It goes past the rest position, okay, but it's slowing down a lot, and then the spring pushes it back, and it ends up just right there at rest position and stops. And no more oscillations happen, okay? Any less friction and it would keep going and then oscillate back and forth and back and forth. Any more friction and we never would have gotten past the rest position to begin with. So that critically damped situation is where we have just enough friction so that we go past the rest position and back, but not enough friction to allow for any further oscillations. And I hope that agrees with some physical intuition you have about how springs work. Okay. So given just any kind of differential equation, second order differential equation, you can determine without solving the whole thing, you can determine which of these situations you're in, underdamped, overdamped, etc., just by looking at the trace determinant plane and deciding, are you on the parabola, are you off the parabola, are you on the y-axis, are you off the y-axis? Okay, I'm gonna flip over for a second back to my, I already close it. Shoot. Oh, there it is. Back to my WebWorks screen. So hopefully, are you seeing my, oh no, you're not seeing it. There we go. You see my WebWorks screen now? Yeah, good, okay. Your next homework assignment is homework 12. If you look at homework 12, these are all situations where we have a second order differential equation, and you can tell if things are overdamped or underdamped, etc. Okay. In each of these situations, you can look at the equation and tell which graph it is. So it looks like I'll tell you what, I'm going to pull this one off. Don't look at this first one. I'm going to pull that off before it gets released to you. Let's look at the other two. Oh, here we go. This is good. So here are the steps to do a problem like this. Okay, so part A, we've got x double prime plus 4x equals 0. So the first thing I would do is I would convert that to a 2x2, a system of two linear equations. That gives you a 2x2 matrix. I'd compute the trace and the determinant of that matrix. That tells me where we are in the trace determinant plane. Okay, and if I see a center tangent, see if I'm on the y-axis in the trace determinant plane, that tells me the oscillations just go around this circle. There's no friction, which means the oscillations don't die out at all. So which of these four pictures would you say is a picture where the oscillations don't die out?
2.
Yeah, that would be number 2, right? So if it's undamped, I'm on the y-axis in the trace determinant plane, then the answer would be 2. Which one of these would be overdamped? Sorry, underdamped. So I've got some oscillations, but they die off. So I'm above the parabola of the trace determinant plane. Yeah, Michelle? Oh, 4. Good, Michelle. I thought you had your hand up, Michelle, but you're doing 4. Good. Good. In situation 4 there, we've got the oscillations. It continues to oscillate, but they die out, right? So that tells me we are actually above the parabola there in that second quadrant. Situation 3 is where it's overdamped. Things just die off. Okay, so again, knowing where you are in the trace determinant plane tells you that. Situation 1, where the oscillations increase, that's not going to correspond to mass on a spring. So not all of these differential equations correspond to this physical situation or mass on a spring. We will see situations in the next chapter where you have what's called forcing, where you introduce any energy into the system. Like if you have a pendulum, and you have a little kick happening every time the pendulum swings, if that kick is big enough, then the oscillations get bigger and bigger and bigger. And that'll be something like what happens in situation 1 there. Okay. So that's problem 2 on homework 12. Again, I'll pull off problem 1. Problem 3 on homework 12 is, I'm going to pull that off too. Now that I'm looking at these, I'm just going to give you a single web work problem. You'll just have to do that problem to yourself. This will be the only web work problem, will be this one. Okay. And again, use the trace determinant plane to do that one. In fact, while I have you all with me, I'm just going to pull those off right now. Delete, 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 save changes. Yes, you just have one problem on web work for homework, which is just, oops, just that one problem we just talked about. Okay. Let's go back to my iPad screen. Another way you can use the trace determinant plane is by looking at various parameter solutions for systems that have, sorry, I gotta every time I share my iPad screen, I gotta rearrange the windows of my computer so I can see you well. There we go. Another way to use the trace determinant plane is by looking at one parameter families of systems. So the book's got a nice example just to start out with, just to kind of show you what can happen. Let's look at a matrix, the following matrix, -2, A, -2, 0. So again, I've got some physical system, but that physical system has some either unknown parameter, I don't know about it, or some parameter I have control over. And I want to figure out what value that parameter makes my system behave the way I want it to behave. That's a sort of typical engineering application. I'm designing an airplane wing. I have control over the stiffness of the wing, and I want to, set that stiffness parameter so that the wing vibrates as little as possible, that sort of thing, okay? So we've got control over this parameter, and we want to see what the various behaviors of this system might be depending on the parameter. So what you do is you plot all the possibilities in the trace determinant plane depending on that parameter. So real quick, what's the trace of this matrix? Quick.
-2.
-2, what's the determinant?
2A.
2A, good. -2, 2A. So again, I'll draw the trace determinant plane. Here's this parabola. Okay, now I want to plot all the points that look like -2 on the t-axis and 2A on the d-axis. Now A is a variable, so I've got any y-coordinate at all, depending on what A is, but my x-coordinate is fixed at -2. Right? My horizontal coordinate is -2. My vertical coordinate can be anything depending on what A is. All right, so what does that look like in the trace determinant plane? Vertical value is -2, horizontal value can be anything. So describe for me where I am in the trace determinant plane.
It's just a horizontal line at -2, right?
Good, yep. So right over here at -2.
Or sorry, vertical line.
Sorry, yeah, vertical line. The other horizontal. Yep.
Yeah.
Where the trace is -2, then the y-coordinate can be anything. So I get this vertical line. So depending on the value of A, I could be anywhere. Where are the values of A that land me on this parabola? And just remember, the parabola is the place where d equals t squared over 4. So how do I figure out where, what the value of A is that'll get me on the parabola d equals t squared over 4? What do I do?
Plug in -2 for t.
Yeah, plug in -2 for t and 2a for d, right? This goes there, and this goes there, right? So that gives me, what does that give me? That gives me 2a equals -2 squared over 4. -2 squared over 4 is just 1. So what's a? A is just 1 over 2, right? It's just a half. So that point corresponds to where a equals 1/2. What about this point over here? What is a there?
0.
Yeah, that's the point where d equals 0. And if d equals 0 and d is 2a, that means a has to be 0. Okay, so that's the point where a equals 0. So when a equals 0, I'm right there on the t-axis. When a equals 1/2, I'm on the parabola. Okay, where do you think, just make a guess now, what do you think the values are for a if I want to be above that parabola?
Just a greater than 1/2.
Yeah, a is to be bigger than 1/2. Down here, I get a is less than 0. And then here, 0 is less than a, less than, sorry, not less than or equal to, less than 1/2. Okay. All right. So thinking about parameters for this system, again, if you're an engineer, you probably have control over these parameters. If you're a scientist modeling some horrible worldwide virus outbreak, maybe you don't know what the parameter is. So you want to see what parameter value is likely for A given the data that you've observed. Okay, that's what scientists do. They go out and observe data and they try to adjust their models to fit that data. So you would adjust the value of A to fit the data that you observed. So if you think about varying values of A, when A is very negative, when you're below the x-axis, what kind of system are you seeing? What does the phase portrait looks like for negative values of A?
A saddle point.
Yeah, we're down there in the lower half of the trace determinant plane. So for negative values of A, you would see a phase portrait that looks like a saddle. As you increase A and A hits 0, now you're on the trace line, the trace axis, and those are the places where you have a 0 eigenvalue. So you should know what that picture looks like. If you increase A just a little bit more, and it's between 0 and 1/2, right? We're above the t-axis but below the parabola. So what do things look like there?
The sink.
That's a sink, good. Then we hit the parabola at A equals 1/2, and we have a repeated eigenvalue situation. And then we keep going, and we're above the parabola. And what kind of thing do we have there?
Spiral sink.
Spiral sink, right? So we go from saddle at the bottom of the picture, we transition through this critical value where A equals 0, and we go into this region where we have sinks, and then we pass 1/2, and we have spiral sinks. Right? So we can kind of plot that. If you just think about the A axis, there are these critical points where A equals 0 and where A equals 1/2. Down here we have saddles. Here we have sinks. And here we have spiral sinks. Okay, and then we have these critical transitional places where things are weird, right? That first place where A equals 0, that's where you have a 0 eigenvalue. And this place is where you have repeated eigenvalues. In some sense, in nature and in engineering, you don't see those critical values, right? No natural system is going to allow you to set a parameter at an exact real number. You're always going to be off by, whatever your margin of error is. You're never going to hit that exact real number, which means if you're trying to set a equals 0, you're always going to have some tolerance. So you're either going to be on one side of that or the other. You're either going to really be a saddle or a sink. And if you're trying to hit a equals 1/2, you're never going to hit it exactly. It's either going to be a sink or a spiral sink. That's why I keep saying like those repeated eigenvalue case isn't so important, because in nature it never happens. You never hit any particular value exactly. Good. So does everybody understand? I hope when you have a 2x2 system where there's an unknown parameter, that's going to confine you to one line in the trace determinant plane, which will just confine you to a certain number of different types of behavior. You won't see all possible behaviors on that one line of values. Good? All right. So I'm going to assign you some problems out of the book. In addition to the one web work problem, I'm going to assign you 2 different types of problems. One's going to be on these different parameter values. So that is, I'll write it down. So you can always come back to the video if you don't write it down right now. This is in section 3.7. And you should look at problems 2 through 7. And at the very least, just do the odd ones, because those you have the answers to. And if you want more practice, you could do the even ones, although you won't have the answers to those. Okay. All right, one more topic, which is, again, looking at specific types of systems, specific types of matrices. But now there's 2 parameters that can vary. So these are problems 9 and 10 in the homework. So I will do problem 10 right now, but also I want you to do problem 9. So, but we're going to do problem number 10 right now. Okay, so problem 10 says, let's say I have the following system: A, B, minus B, A. Okay? So depending on what A and B are, the question is, where in the trace determinant plane might I be? So again, I mean, think of it, you're an engineer or something, and you're putting together gears and springs or capacitors and resistors if you're an electrical engineer, or you're some sort of scientist and you go out and observe some population model and you write down your modeling assumptions and you find that your system is going to look like this somehow. Not clear how this arises, but for some reason, when you write it as a 2x2 matrix, the top left and bottom right entries are equal, and the top right and bottom left entries, one is the negative of the other. So now let's look at this trace determinant plane analysis. So the trace is the sum of the values on the diagonal, A plus A, 2A, and the determinant is A times A, which is A squared, minus negative B times B, which is plus B squared. Okay, 2A and A squared plus B squared. Got it? All right. So now I gotta somehow figure out where the hell on the trace determinant plane I might be if the trace is 2A and the determinant is A squared plus B squared. Anybody have any ideas how you might figure that out?
Well, the A squared and B squared have to both be positive, right?
A squared and B squared have to both be positive. So I definitely know I'm above the T line.
You're in quadrants
Yeah.
1 or 2.
1 or 2, quadrants 1 or 2, that's right. I know that the determinant is positive. Okay, so I'm definitely above this line. But it'd be nice to be able to say where I am in relation to this parabola. Anybody have any ideas?
Do you look at different cases of A and B?
You could. Here's what I would do. If I was trying to plot things on the XY plane, I would try to get Y as a function of X. Okay, and then I know a lot about how to plot functions. So if I'm trying to plot something in the TD plane, you should try to get D as a function of T. How are you going to do that? How are you going to get D as a function of T?
You could rewrite the d equals a squared plus b squared in terms of a, and then plug it into the t equation.
Good, good, right? This is telling us, or do it the other way. Do it the other way. Let's write a as a function of d, and then d is a squared over 2, which is t squared over 4 plus b squared. Okay, d equals t squared over 4. Where's, let's say b were 0, so let's forget about b just for a minute. Okay, what is d equal t squared over 4? Where is that in this plane?
Parabola.
That is the parabola. That's the defining equation for level. So when b is 0, we're right here on this parabola. That's when b is 0. Now, what if b is anything that's not 0? Either positive or negative. What's happening to that parabola? Good. Michelle, I see you do it. It pushes it up. If b is any positive or negative value, I'm adding that to t squared over 4. So I get other parabolas here. And let's see, oh, sorry, t can be positive or negative. So I get the whole parabola when b is 0. And when b is anything, I get other parabolas. So the bigger the absolute value of b is, the keep hitting keys on my keyboard accidentally. Sorry. I've got my iPad right next to my keyboard. All right, there we go. The bigger the absolute value is of b is, or the bigger b squared is, the further up from that parabola I'm going to be. Right? So, if t, now we can think about different situations, right? We know we're either going to be on the parabola when b equals 0, in which case we have a repeated eigenvalue situation, or we're going to be above the parabola. If we're above the parabola, then we can only see a spiral sink, a spiral source, or a center, right? So when b is positive and t is 0, where are we? Let's look at some different cases. So these are all situations where b is not equal to 0. We're above the parabola, okay? And we're on this side versus this side when 2a is positive or negative, right? So that means a is positive or negative. So if a is less than 0, we're on the left. When a is greater than 0, we're on the right. And when a, we're right there in the middle when a equals 0. Right? And this whole region is happening when b is not equal to 0. So as long as b is not equal to 0, then the kind of system we have is completely determined by the sign of a. Right? If b is not equal to 0 and a is negative, we have a spiral sink. When a is 0, we have a center. And when a is positive, we have a spiral source. The problem, the homework problem, let me read you the instructions for the homework problem. The instructions for 9 and 10 are exactly the same. So for problem 9 on the homework, you're going to be asked to analyze this system, A, B, B, A. Very, very similar, right? We just did A, B minus B, A. You're going to do A, B, positive B, A. And the instructions say the following. In the A, B plane, identify all regions where this system possesses a saddle, a sink, a spiral sink, and so on. Okay, so they actually now, they don't want you to draw the trace determinant plane. They now want you to draw the AB plane. So let's do that for the problem we just did, right? So we're going to draw the AB plane. And now we've got to think about all of these situations, right? As long as b is not 0. So where are the places where b equals 0? In the AB plane.
It's the a-axis, right?
That's the a-axis, right? So on the a-axis, we're on the parabola in the trace determinant plane. And so everywhere on the a-axis, that's where we have the repeated eigenvalues. Okay, now as long as b isn't 0 and a is positive, then we have a spiral source. So where is that in the AB plane? B is not equal to 0 and a is positive.
Quadrants 1 and 4.
Good. Quadrants 1 and 4, right? Spiral, source, spiral. All right. And what about B non-zero, but A is negative? The other two, right? And what's that remaining case? Where is A equal to 0 and B not equal to 0?
Oh, on the B axis, is it
Good.
as center?
Good. Okay. So I just want you to compare this problem. So this problem up here is where we have one parameter, a one parameter system, and the only parameter there is this number A. And so if I want to understand everything that can possibly happen, I drew a picture of the A, the real line representing A, and I labeled various intervals on the real line with the different kinds of behavior for my system. If I have a two-parameter family, now I have A and B, and so if I want to get a hold of what everything can happen for different values of A and B, I've got to plot the entire AB plane and just label the different regions of this plane accordingly depending on what happens to my system. That makes sense? So you just have one homework problem where you'll have to do that. Problem 9. I intentionally gave you an odd numbered one so that you would have the answer to check yourself with. Okay, so again, on the homework, number 9 is a system with an A and a B, 2 parameters, and 2 through 7 are systems with a single parameter. Okay, so I encourage you to do those textbook problems. And then you have that one Weber problem as well, that's just about second order equations, converting those into first order systems and trying to identify which picture is which by using the trace determinant plane. Any last minute questions? We're 2 minutes over time, so.
When will we be having our exam?
Great question. I don't know yet. I'll let you know. That's a really good question. Oh, I do want to show you one more quick thing, which is where I'm posting the videos that I'm doing. So if you go to my webpage, again, just Google David Akman. You may have to add Pitzer to your search string. And you can find your class right here, Math 1/2. And I just added a section here down at the bottom of the page for the lecture videos. So last time we did the trace determinant plane. And as soon as I'm done talking, then I'll upload the video of everything I just said. You can see. Yeah, there's me from last time, looking goofy. This initial condition of -2. Good. So if for some reason you can't make it to class on time, you can always go back and watch the video from that class day. Or if I say anything that confuses you and you want to watch it again, then feel free to go back to the video. We good?
Yes. Thank you.
Okay. Good luck on your homework. I'll see you all Monday.
See you Monday.
Okay,
Yep.
thank you.
Thank you.
Sure.
Thank you.
Bye.
Bye.